Hello everybody. Alright, well we're going to talk about dynamic binding now. Now, when we were talking about explicit and implicit bindings, these are static bindings. Alright, so we were just talking about static binding of type, and now we're talking about dynamic binding of type. So when we have dynamic binding of type, the type is determined at runtime. It may change at runtime as the program executes. In fact, the type may be rebound at each assignment statement. So here's an example using JavaScript. Alright, so I've got a variable that's called list, and I'm going to set that equal to the following list: 10.2, 3.5. So there's two elements here in my list. Alright, now I say list is equal to 42. So here I had list was an array of length 2, and now I have list is a scalar variable. So what are some advantages to this type of approach over static type binding? Well, one thing is I guess one thing is that this mechanism lends itself to generic programming. You can imagine if you bought a or devised an algorithm to do anything, like even say like a sort or something like that. Let's say you could do a sort. Well, you know, the sort is going to take a particular type of collection and sort the elements in the collection. Say it's a collection of integers. All right, but if you're careful about how you write the sort, then you're going to be able to sort any kind of list, as long as you have some way of comparing the elements in the list. So here we have a list of integers, but there's no reason why that list couldn't be a list of string, or these aren't integers, I'm sorry, list of numbers, decimal numbers. But there's no reason why that list couldn't be a list of strings, or a list of integers, or a list of, you know, some other data type. And as long as you can compare those two data types, you're going to be able to write your sort code and pass in any type of list and have that list sorted, because there's no restrictions on the type of the list and the type of the elements that are being passed into the sort. Okay, so that's an advantage. There's some disadvantages though. And those are, there are a couple of them. A lot of them float around the idea of performance. There's a performance cost. And the performance cost is in a couple of areas. First of all, you have to do runtime type checking. So what does that mean? Well, that means if, I is equal to hello and j is equal to 2, if you attempt immediately following this to say I times j, you're going to have a problem. And in some scenarios, I times j is perfectly legitimate because I might be set to an integer. In other scenarios, I is a string and j is an integer. And so you can't know until you actually execute, if you're doing runtime type binding, you can't actually know if I times j is valid until you actually get to the expression I times j, and you look at the current type of I, and you look at the current type of j, and you look at the operator multiply, and to see if it's valid to multiply I and j together. So there's a cost associated with that, because pretty much every statement that gets executed is going to have runtime type checking. You don't have to do that with static type checking because it's done at compile time. So when the programs run, you don't have to worry about type issues. Okay. Another issue is runtime space management. So with runtime space management, what's going on is every variable, like the variables I and j up here, every variable has to have an extra field associated with it. It's not just I is not just, a string, but there's a field associated with the variable I that indicates its current type. And so that takes up space, and same with j. J is not just an integer, but there's a field that indicates what j's type is. So that wastes space. I'd also argue that there's a software engineering cost as well, and that is that if you think about all of the problems that you run into when you write code, and it's whenever you're trying to build a system, there's always human error involved, and what you want to try and do is eliminate as much human error as possible automatically. All right, so using tools to eliminate those errors. And now the tools are not going to be able to eliminate your logic errors, but there's a lot of syntax errors that compiled code gets rid of by the simple act of compiling the code, right? The compiler runs, it identifies syntax errors, and then you fix those syntax errors. And sometimes in the act of fixing those syntax errors, you realize that you have a fatal logic error flaw. But when you're using a dynamically typed language, you lose that benefit, that tool benefit that's identifying syntax errors for you. So you have to discover the errors in an ad hoc fashion as chunks of code that you've written are executed. And that's much more challenging to do. So there's a software engineering cost. All right. Now, this is something that's kind of interesting. So we've got dynamic binding of type. We have static binding of type. But I have another topic that's somewhat related to this. I think it's worthwhile spending a few moments on. And that's called type inferencing. So with type inferencing, what you're attempting to do is you're attempting to infer a type based on expression. And there are languages that will allow you to do this. And one example is in a language called ML, which is a functional imperative language hybrid. So it's both functional and imperative. Okay, so here's an example. All right, I'm going to write this. I mean, you've never seen this language before, but I bet you can tell me the type that this function returns. So here's a function. It's like a method, but and it returns a value. So function circum r equals 3.1415 times r times r. Now, do you know, based on this, what the type of r is? Can you infer it from this function definition? And the answer is yes. If the expression has a real in it, or a floating point number, double, in ML it's called a real. If the expression has a real in it, then it makes sense that everything participating in this expression would be a real. So we could say, hey, r is a real. This r is a real, and also the entire expression is a real, so the expression itself returns a real, so the function returns a real. So we can say r's type is real, and we can say that circumference also is real. All right, how about, okay, so let's take a look at another example. This is a function times 10, and it takes x equals 10 times x. So here, what's x? What's x type? Well, we can infer that x's type is an int, right? Because 10 is an int. And that's all we have to go with. So we're going to infer that it's an int. And times 10, since we've got an int times 10 is going to return an int as well. All right, let's take a look at this one. So function square x equals x times x. So in this situation, we cannot infer the type. Of x or the type of the function. Because it could be real, could be an integer, I mean, who knows? So, what you can do in situations where the type can't be inferred is you can be explicit. So function square x, which is a type real, equals x times Okay, now we know x is real, therefore this expression is real, therefore square is going to be real. Awesome. Okay, I'm going to stop this, and then we're going to talk about address binding next.